Swayam Prabha. Digital India. Educated India.
Good morning. We will continue our discussion of multiphase flows and see one possible route by which we can model these sprays. Before we go to modeling multiphase flows, what I want to do is try to see if we can recap some of the information we learnt earlier and concepts we learnt earlier with regards to probability density functions. So, our old definition of a probability PDF, if I define an F, I will use R for the radius of the drop, and I will write down the nomenclature. Defined such that this is the probability of finding a drop in the range R to R plus dr and velocity v to v plus dv and in the spatial location x to x plus dx. So, that is, let us just quickly understand what this means. If I take a spray and I will plant my coordinate system, just to, since we are now talking about a real physical system and modeling a real physical system. If I take a tiny volume element and imagine there is a bunch of these drops inside here, then if I take f, this f times this probability density f of r comma v comma x semicolon t, t is time of course here, is basically given by the probability of finding a drop in the radius range r to r plus dr and velocity range v to v plus dv. So, we should be clear about what this vector v to v plus dv means. So, I will write that out. V to v plus dv is the same as saying or rather let us be, it is easier to define the dv vector. dv is equal to dv1, dv2, dv3, which is the velocity components in the 3 directions. So, it is like a little tiny volume in the velocity coordinate. So, if I take a velocity, if I take a drop of radius r, if it is, and I can easily understand what the meaning of r to r plus dr is. So, it is like 50 to 51 microns. What the volume element in the velocity coordinate, this dv vector given by the product of dv1, dv2, dv3 means finding a drop of velocity, let us say 10 to 10.1 meters per second in the x direction, some 1 to 1.1 meters per second in the y direction, and let us say 5 to 5.1 meters per second in the z direction. So, a drop satisfying all 3 conditions is what will fall inside this dv element. Likewise, dx is easier to understand, we have been trained to understand this since high school. I will refer to these by x1, x2, x3, it makes more sense. This is dx1, dx2 and dx3. So, so this is easier to understand because it is physical space. It is the space of space in the spray like a little tiny volume, and I am looking at all the drops that fall inside this volume, that is my starting point. Of all the drops that fall inside this volume, I want to look at the drops that have size r to r plus dr and have velocities between v to v plus d1, v1 to v1 plus dv1, v2 to v2 plus dv2 and v3 to v3 plus dv3. That is like a tiny, if you can think of this now as a volume element in the velocity coordinate. So, this is I want to make sure we are all on the same page. We are used to spatial coordinate and volume in the spatial coordinate. We are now defining a velocity coordinate and defining a volume in that velocity coordinate. So, I can now define any other coordinate just like this, and I can define a volume in that coordinate. The reason I have a volume in the velocity coordinate is because velocity is a vector. So, I require 3 components to describe the velocity vector, and it naturally forms a volume in the velocity coordinate. Whereas, if I took radius is a scalar and I just need r to r plus dr. So, essentially I am still defining a volume, but it is volume in a one dimensional space. Okay. So, r to r plus dr defines a volume in 1D space of the scalar quantity radius of the drop. dV defines a volume in the in the velocity coordinate in the 3-dimensional velocity vector space dv1, dv2, dv3. dx defines a volume in the spatial coordinates in the spatial coordinate vector space d1, dx1, dx2, dx3. So, what we have done is we are used to space as having coordinates, we are now introducing velocity as also being a coordinate. That is a fundamental shift in the way we are going to look at these models, and I think there is a reason we do that. We will come to that maybe later on. So, the moment I have made this, I have defined this multivariate probability density function f with r, v and x as the independent coordinates. So, this is in 7 coordinates and time as being a parameter. So, we are not defining, I can define an instantaneous probability density function. So, at this current instant of time, if I gather all the drops that are in the spatial location dx, x to x plus dx and parse them into radius bins and velocity bins, this gives me the multivariate probability density function. Now, we looked at this even when we defined multivariate probability density functions. The fact that the f at this point is clearly not the same as the f at another spatial location. Okay. Now, f is a function defined in this 7-dimensional space of 3 velocity coordinates, 3 spatial coordinates and the radius of the drop. So, typically we will use the word external coordinate to define the spatial coordinates. Those are like obvious to us, they have been, we have learned that from Cartesian geometry days. These velocity and radius are internal coordinates. Now, I can continue on and define many more internal coordinates, as many as I need to completely determine the state of a single drop. Say for example, we talked about this in our earlier lecture. If I have a mixture of, let us say, methanol and ethanol that I am spraying, then the fraction of ethanol in a given drop is an internal coordinate of that drop. I can define a probability density in that internal scalar coordinate. So, I can now define concentration in a general sense of some n dimensional mixture as being an n vector as being an n vector, and I can continue this argument forward. Okay. So, I just want to bring the distinction between external coordinates and internal coordinates in the way we are going to look at sprays. So, now we want to write an equation that describes the evolution of f in space time and the velocity coordinate. So, the velocity is now an independent coordinate, just like space. We are not going to make any distinction between velocity and space. It is like at this point I have a certain drop at this location moving at this velocity. This position and velocity are both characteristics of that drop, they are independent variables. There could be other dependent variables that fall out of this, we will look at those. Okay. So, now let us go back to this idea of a simple co-moving derivative and see what we are used to this. Say if I have some function f or some function g which is a function of x and time, we write a co-moving derivative of g this is what we very often refer to as capital dg dt. where u is the velocity, scalar velocity in the x direction. Okay. This comes from basically defining g as a field in x and time. So, essentially if I had this g is a property everywhere in x and time, and u defines the transport velocity at every point in space and time. So, u is also a property of x and time. That is generally how we understand fluid mechanics. Okay, and this comes from basically defining velocity as a field, not velocity as a property of a particle or property of the material. Okay. So, if I define velocity as being a field variable depending on the spatial coordinate and time, whatever material particle passes through that point in space and time acquires that velocity. That is our basic assumption on which our hydrodynamics and Navier-Stokes equations are built. So, if I now take that forward, and if I have x and t as my independent variables, this is my co-moving derivative. If I continue this forward, if I define f like we have here is a function of r, v, x and t. So, for this general probability density function, how do we write the co-moving derivative and what does that mean? This part is fairly straightforward, right. So, since f depends on since f is a function of the spatial location x y z or x 1 x 2 x 3, I could have an advection of this property f. F is just like our old g. Okay, any property which is a field which is defined as a field, which is defined as a function of x and time, can be advected through that in that spatial coordinates and time by their respective velocities v1, v2, v3. So, if I have v1, v2, v3 as the velocities at a given point of this material f, of this property f, then the partial derivative of f with respect to time plus v1 df dx1 plus v2 df dx2 plus v3 df dx3 gives me the rate of advection in space and time. But we now have additional coordinates in terms of v and r which are now defined as our independent coordinates. So, how do we account for those? You require additional terms. What does this mean? If f1, f2, f3 is a force vector per unit mass acting on the population of drops. Okay. So, just like I require velocity which has units of meters per second, velocity has units of meters per second to move the to advect the probability density function in the spatial coordinate which has units of meter. Okay, so, if the spatial coordinate has units of meter, the corresponding velocity with which the property is advected has units of meters per second. If the internal coordinate has units of meters per second, the corresponding property, the corresponding let us say vector by along which this property is advected in that the probability density function is advected in the velocity space will have to have units of meters per second per second. Okay, so, essentially this force is I mean F1, F2, F3 is the force vector per unit mass, which is what we know as acceleration. So, if there is a force per unit mass acting on this population of drops, that is going to cause movement of this particle in the velocity coordinate. I want to make sure we understand this, and also let us take a very simple example, one we are familiar with from high school. If I take let us say a block of mass m being pushed by a force F, let us say it is initially moving at some velocity v. Okay. So, the acceleration we know is F over m, and we are only going to look at one dimension, one spatial coordinate. Okay. So, one way to look at, say for example, it is currently at this location which is x equal to 1, let us say, or x equal, right. So, if I look at the probability density function at this x equal to 1 or the probability density function in space, it is a Dirac delta function at x equal to 1. That is, I have a mass at x equal to 1 and everywhere else there is no mass. So, we will just looking at a point mass, let us say. Okay. So, I have, if I look at the probability of finding particles or number density of particles, we are used to number PDFs, and we will define this F also as a number PDF. The number PDF at every location other than x equal to 1 is 0, and or rather the number probability at every other location is 0. So, if I take a location from 0 to 0 plus dx, whatever dx may be, the number probability in that spatial location 0 to 0 plus dx is 0. The number probability in 10 to 10 plus dx is 0. The number probability from 0.95 to 1.05 is 1. So, I have one particle and there is, so there is a probability of finding a particle around 1. So, in the limit of that dx shrinking to 0, we get our probability density function, and that probability density function when plotted in the spatial coordinate takes the form of a Dirac delta function at 1, and basically it is like a very sharp peak going towards infinity at 1, with the area underneath this curve being bounded, being equal to 1. That is the meaning of a Dirac delta function. And so, this is the probability in, this is a PDF in the spatial coordinate. If I plot the same PDF in the velocity coordinate, if it is initially moving at some velocity v0, so I am now disregarding space. I mean it is a little trivial to talk of PDF of one particle, but I thought this example should illustrate at least the idea of an internal coordinate as being not very different from an external coordinate. That is my objective here. I can look at, if I have, let us say, a bunch of particles, we all understand how to create a PDF in that velocity coordinate. If I do a similar PDF of this one particle, there is a probability of finding a particle at V0 and no other velocity, right. So, I can at some velocity V0 there is a Dirac delta function that says, essentially says, all my particles have one velocity V0, all in this sense is 1, but that is immaterial to the PDF. Okay. So, all my particles in the system have one velocity V0, and I can actually make the argument that this is a mass containing many particles and they are all moving at the same velocity, they are all at nearly the same physical location x. So, I mean these things can also apply physically to that system. Okay. So, now how do I move this PDF in the spatial coordinate? By the spatial velocity. So, if the particles have a spatial velocity, if this is the PDF at time t, at some other time t plus delta t, this PDF shifts to 1 plus V0 dt. So, at some future time t plus delta t, t plus dt, this same Dirac delta function has moved to a new location x1. So, the probability density function in x coordinate is now given by delta. So, if I define f of x at time t, this is given by the Dirac delta function at x minus 1. The probability density function at t plus dt is given by this x minus x1. Okay. So, this t plus, so all we have done is velocity in the spatial coordinate has advected this PDF from being peaked at x equal to 1 to some x equal to x1. Similarly, if I have a force acting on this system and the acceleration is f over m, the f of v at some time t, the f of v, we are only writing a probability density function in a single coordinate just to sort of understand what is happening, and in this case the multivariate or the bivariate probability density function of x and v is the product of these two, whatever we are writing here, we will show that also, right. So, I know that at some time t I had a Dirac delta function defining my probability density function in the velocity coordinate, and the Dirac delta function was a peak at v0, the value v0. At some future time, what would this look like? Okay. So, just as we said, we updated its position due to the velocity. We say we update the velocity due to the acceleration. So, we are in this formulation, the velocity is also a coordinate along which motion is possible due to acceleration. Okay. I want to take one more last little bit of complication. Let us say this block was growing. So, let us say initially this is of some mass m, or we will say for example of some size x, some size L. It is a cubic block or of some size L, let us say, and I have a little mass accumulating on here at some L dot or some V dot, some volume is being added to this block, and as a result its size is also changing. So, this is just like a condensation or an evaporation process in a droplet, right. So, what I can now say, I can do something exactly similar. So, let us say initially it was some size L0, L0 is the size of the particle at time t. And if I now take at the next time the same probability density function in the size coordinate,